Hello everyone. In this video, we'll be covering concepts from the course of Chemistry 1412, also known as General Chemistry 2. As you can see, the concept that we're covering in this video is going to be a final exam review. So this video will consist of exam 1, 2, and 3 material because most of your classes will have a cumulative final. I break down this video into those 3 sections, and in those sections, I specify which chapter I'm covering. However, do keep in mind that your professors can break them up separately based off how they want to set up their exams. So I might have a certain chapter on exam 1, however, you might not have had that chapter until exam 2. Do keep that in mind. However, it shouldn't make much of a difference because since we're around finals time, you should have covered just about all the information. So the first section we're covering is Exam 1 Sample Problems. In this section, we'll cover Chapter 12, which covers intermolecular forces, Chapter 13, which covers properties of mixtures, and Chapter 16, which covers kinetics. So, Example 1. Liquid sodium can be used as a heat transfer fluid. Its vapor pressure is 40 torr at 633 degrees Celsius and 400 torr at 823 degrees Celsius. Calculate its heat of vaporization. So I'm going to move over to my boogie board, and we're going to start working through this problem. So because it told us to solve for heat of vaporization, we know we're going to have to use the following equation. It's going to be Ln of P2 divided by P1 equals negative delta H, and remember delta H is heat of vaporization, divided by R times 1 over T2 minus 1 over T1. So this is the equation that we're going to use, and we now need to be able to determine what our variables are. So our P1 is going to be that 40 torr, which means our P2 is 400 torr. For those that didn't know, P represents pressure. The next one is temperature. So our T1 is 633 degrees Celsius, but we need this in Kelvin whenever we plug it in. So it is going to be 906.15 Kelvin. And then T2 is going to be 823 degrees Celsius, which is 1096.15 Kelvin. Our R is our constant, and it's going to be 8.314. So just remember that. That's the R value that you're going to use when using this equation. Another important thing to remember is when you're plugging delta H into the equation, it needs to be in joules per mole. So since we're solving for delta H, we're going to solve for it in joules per mole. However, when we go to represent it in our answer, delta H needs to be in kilojoules per mole. However, most of the time you're going to have a multiple choice answer, so you can just look at the units that they provide. All right, so now that we know our variables, we can start to plug it into our equation. So we have Ln of 400 divided by 40 equals negative delta H divided by 8.314 times 1 over 1096.15 minus 1 over 906.15. So we now have it all plugged in, and we can start solving to be able to isolate our unknown variable. So when we plug in Ln of 400 divided by 40, we're going to get 2.30. And then I'm just going to write this back down here. And then when I plug the temperature, I'll get negative 1.91 times 10 to the negative 4. And then you simply rearrange this equation to solve for delta H. So remember, if you're multiplying by something, to get it to the other side, you have to divide. And if you're dividing by something, to get it to the other side, you have to multiply. So our delta H will equal 99,964.88 joules per mole. However, like I said, we don't want to keep it in joules per mole. Delta H prefers to be in kilojoules per mole. So we need to do a basic conversion to get from joules to kilojoules. And if you don't remember how to do conversions, I highly suggest you look back at your old Chemistry 1 notes, or you can look at Khan Academy. They have good videos to show you how to do conversions. So when we convert delta H to kilojoules, we'll end up with 99.9 kilojoules per mole. And that will be our answer. All right, now we can move on to example 2. It says, if C2H6 is burning at a rate of 0.20 moles per liter second, calculate the rate of change of CO2. And so we have the equation, or the reaction, C2H6 plus 7O2 yields 4CO2 plus 6H2O. So I'm going to move back over to the boogie board so that we can solve it. So I went ahead and I wrote out our formula. And they gave us the rate of change for C2H6. They said the rate for C2H6 was 0.20 moles per liter second. So we need to compare this to CO2 because they want to know the rate for CO2. What we notice, or what we need to look at, is the coefficients for both of the two. So because there's no number in front of the C2H6, we know that that represents a 1. So we know for every 1 C2H6, we have 4 CO2. So CO2 is going to be 4 times larger than C2H6. So the rate will be 4 times larger. So we take the rate that we're comparing and we determine how much bigger or how much smaller it is. So in this case, 4 times bigger. So we're going to multiply times 4. And this will give us a rate of 0.80 moles per liter second. And this is going to be the rate of CO2. For number 3, which of the following substances have a hydrogen bond between molecules? So remember that a hydrogen bond has to be with either a fluorine, oxygen, or nitrogen that is bonded to a hydrogen. So hydrogen bonds are FON, so S-O-N. So we need to look and see what are these hydrogens bonding to. So E is pretty easy to cancel out. You have a hydrogen and an iodine, so you know that that doesn't fit our rules, so we can cancel E out automatically. By looking at our other options, we see that our CH3, which means we have 3 hydrogens connecting to this carbon, so the carbon and hydrogen are forming a bond, and this fluorine, this right here, shows that the carbon and the hydrogen are bonding to each other because the 2 hydrogens will be on either side of this carbon. So we know it's still bonding to carbon, so that's not an option. If we look at C, we have hydrogens connecting to this carbon, these 2 hydrogens connecting to this carbon, but we see that we have an oxygen connecting to the hydrogen. that fits our rule. So far, we think C is our answer. However, we can go ahead and check the others just to make sure that there wasn't a mistake or that we need to double check ourselves. Here, CH3, so we have 3 hydrogens connecting to this carbon. This carbon connects to the oxygen, same thing with this carbon, and these 3 hydrogens will connect to the carbon as well. So the hydrogens aren't connecting to the oxygen, it's the carbons that are doing that. So we know that this is not a hydrogen bond. And then finally, we come over here. We notice that we have 3 CH3s. So just like before, because it's set up this way, we know that the hydrogens are connecting to the carbon, and that it's the carbons that are connecting to the nitrogen. So the only option that we have is C as our answer. Example 4. What volume of concentration 14.7 molar phosphoric acid is needed to prepare 25 liters of 3 molar H3PO4? So this one should seem pretty easy. We have a basic chemistry 1 type problem here. So it's going to be an M1V1 equals M2V2. So they gave us the molarity of what we're looking for, so 14.7 molar. We want to know the volume, so that's our X variable, equals, we have a second molarity of 3 molar, and we have 25 liters of that. So whatever our answer is, it's going to be in liters. If your answer choices are in milliliters, ensure that you do a conversion before selecting your answer. So you're going to multiply 3 times 25, divide by 14.7 to get it on the other side, and our X is going to be 5.1 liters as our answer. Pretty simple. And now we have a phase change diagram type question. So hopefully you are comfortable with the phase change diagram. So it says examine the phase diagram for the substance BO and select the correct statement. So for this one, you simply need to go through each answer choice and figure out what is happening. And does this fit what the answer is saying? So for A, it says BO solid has a lower density than BO liquid. This one, you don't even need the diagram to know that that's incorrect. So we know that a solid has the highest density. Right below it is a liquid, and below that is a gas. So your solid can't have a lower density than your liquid. So A is not your answer. The triple point for BO is at a higher temperature than the melting for BO. So remember, melting is going to be from solid to liquid. So our solid to liquid. And we see that our triple point is right here, and that going from solid to liquid, it's actually at a higher temperature than our triple point. So that can't be our answer. For C, BO changes from solid to liquid as one follows the line from C to D. So we said up here is solid, and right here is liquid. C to D goes from solid to gas. So we know that this doesn't fit, so C is not an answer. The next one says that BO changes from liquid to gas as one follows C to D. This is also incorrect. If I was going from solid or liquid to gas, I would be going from liquid to gas, and that's not what's happening. So D is not an answer choice either. And then finally E, point B represents the critical temperature and pressure for BO. So this is our critical point, which means that this is the correct answer. So E would be our answer for example 5. And now we're going to move on to number 6. At 34.1 degrees Celsius, the vapor pressure of water is 40.1 torr. What is the vapor pressure at 85.5 degrees Celsius. The delta H of water is 40.7 kilojoules per mole. So let's move over to our boogie board. Sorry. All right. So we know that we're given delta H, so we know which equation we need to use. It's ln of P2 divided by P1 equals negative delta H divided by R times 1 over T2 minus 1 over T1. And just like before, we need to figure out what our variables are. So our P1 is 40.1 torr. Our P2, we weren't given, so that is our X variable. Our T1 was 34.1 degrees Celsius, which is 307.25 Kelvin. T2 is 85.5 degrees Celsius, which is going to be 358.65 Kelvin. And then delta H. This is a part that a lot of students will get mixed up. We are given 40.7 kilojoules per mole. However, to plug it into the equation, we have to have it in joules per mole. So we convert this to joules per mole, and we'll get 40.7 times 10 to the 3 joules per mole. Or you can put it in extended form, it doesn't really matter. So now that we have our variables, we can start to plug it into our equation. So we say ln, I'm going to put an x for P2, so x divided by 40.1 equals negative 40.7 times 10 to the third divided by 8.314, which is our R constant, times 1 over 358.65 minus 1 over 307.25. So we now have everything and we need to solve for X. So I'm just going to copy this back down. So ln of X divided by 40.1. And because we have everything on the right-hand side, we can go ahead and solve for the entire thing. So solve for this section right here, solve for temperature, and then multiply the two together. When you do that, you're going to get 2.28 as the answer on the right side. We now need to isolate our X variable. So we need to get rid of this ln. To do that, it becomes X divided by 40.1 equals e to the 2.28. This will become X divided by 40.1 equals 9.8. We can then multiply both sides by 40.1 to get X by itself. So X equals 390. And because it's pressure and our P1 was in torr, it's 390 torr. So our P2 is 390 torr. Now for number 8. Methane has a Henry's law constant, so that's an important information right there. It tells you exactly what you are looking for. Oh, sorry, I realized I skipped number 7. So let's go back to number 7 real fast. Aqueous isopropyl ethanol is commercially available at a solution that is 50% isopropyl ethanol. What is the mole fraction of isopropyl ethanol in the solution, assuming this is a 100-gram solution? So for this one, you have to take, or you have to really read into the question. So it says that we have a 100-gram sample. and then its weight is 50%. So we know that 50% or 50 grams is going to be the isopropyl ethanol. So it's C3H8O. However, you have to remember that it said it's aqueous isopropyl ethanol, which means it's mixed with water. So 50 grams of water are also going to be in our sample. And we want to solve for the mole fraction. The mole fraction is moles of solute divided by moles of solution. And remember that your solution is going to be both your solute and your solvent added together. So we need to calculate both of these in moles. So the first thing we can calculate is moles of solute. So remember, solute is the thing that's being dissolved. Solvent is the thing doing the dissolving. So we know that water is going to be our solvent, while C3H8O is our solute. So we need to convert our 50 grams of isopropyl ethanol into moles. So 50 grams of C3H8O, for every 1 mole, we're going to have 60.1 grams. Our grams cancel out, and we'll end up with 0.832 moles of C3H8O. So we now have our moles of our solute, but we have to get moles of solution. To be able to find that, we have to find the solute, or solvent, sorry. So we need to convert our 50 grams of water into moles and then add it to the moles of isopropyl ethanol. So 50 grams of water for every 1 mole. We have 18.01 grams. Grams will cancel out, and we'll end up with 2.28 moles of water. You can either add them separately before putting them into our equation, or you can do it as you go. So we'll put our moles of solute, so 0.832 divided by 0.832 plus 2.28. This is our moles of solution. So this means that our mole fraction is 0.23. And now we can move on to number 8. So methane has a Henry's law constant that tells us exactly what we're solving for, of 9.88 times 10 to the negative 2 moles per liter ATM, when dissolved in the benzene at 25 degrees Celsius. How many grams of CH4 will dissolve in 3 liters of benzene if the partial pressure of CH4 is 1.48 atm? So we're trying to find grams of CH4, given the information that we had. So we know if we have the constant they gave us, the Henry's law constant, we're dealing with the solubility of a gas. So S gas equals our constant times our P, which is pressure of our gas. And we need to find grams of CH4. So what we can do is we take our constant, and I'm going to put it in extended form, so 0.0988 moles, and that was moles per liter ATM. And I need to get this to grams eventually. So I slowly need to start taking out some of my variables. One of the things they told us we had was a 3-liter container. So we have 3.00 liters, which will cancel out our liters. This will give us 0.2964 moles ATM. But they also gave us a pressure, so we can cancel out our ATM as well. So we do 0.2964 moles for 1 ATM. And they told us that our pressure was 1.48 ATM. So our ATM cancels out, and we'll be left with 0.439 moles of CH4. But we don't want it in moles, we want it in grams. So we need to do one last conversion to be able to get our answer. So we take our 0.439 moles, and we set it on our table. We know that for every 1 mole, we have about 16 grams. So our moles will cancel out, and we'll be left with 7.02 grams of CH. So this is supposed to be a 4. And that would be our answer. Number 9. The partial pressure of carbon dioxide gas inside a bottle of cola is 4 atm at 25 degrees Celsius. What is the solubility of CO2? So we know that we're going to be using that same equation that we used previously. It says the Henry's law constant of CO2 dissolved in water is 3.3 times 10 to the negative 2 moles per liter ATM at 25 degrees Celsius. So we write out our equation. So solubility equals our constant times the pressure of our gas. So we take our constant they gave us, which was 3.3 times 10 to the negative 2, and that's moles per liter ATM. And we're going to multiply it by the pressure they gave us, which was 4 atm. Our ATM can cancel out, and we multiply 3.3 times 10 to the negative 2 times 4, and we'll end up with 0.1 moles per liter, because that's the units that are left over. And that is the solubility of CO2. That one's not too bad. It's pretty much a plug and chug. All right, and now we're at example 10. The strongest intermolecular interaction between pentane, which is C5H12, molecules arise from what? So you have to really break down and understand what each of these are. A dipole is going to be the bond between a polar and nonpolar molecule, or dipole. A London dispersion force, we can pretty much find this in just about every single molecule. So B is always an option. Hydrogen bonds, this is going to be when a hydrogen bonds to either fluorine, oxygen, or nitrogen. And then an ion dipole is going to be the bond between an ion and a polar molecule. So one that we know we can cancel out is going to be C, because we know that there is no hydrogen bond in this molecule. The next thing we need to look at is our molecule polar or nonpolar? This one is going to be a nonpolar molecule. So we automatically know D can get canceled out because it's bonding an ion to a polar molecule. The other one we can get canceled out is going to be A, because we had a polar molecule, which we don't have, bonded to a nonpolar molecule or compound, which leaves B, London dispersion forces, as our answer. And now we're going to move on to exam 2 sample problems. which we're going to cover Chapter 17, which talks about equilibrium, Chapter 18, which is acid-base equilibrium, and Chapter 19, which is ionic equilibrium in aqueous solutions. So the first one is write the mass action expression QC for the following chemical reaction. So we have to really look and pay attention when we're solving a question like this. So the first thing that we need to do is remember what QC is. Just like KC, which we've covered in one of our past chapters, it's going to be the concentration of your products divided by the concentration of your reactants, where your coefficients are now your exponents. We also have to remember that we're not going to consider pure solids in our expression, which means that the 2CuI won't be in the expression that we use. So let's go ahead and work through it. So we need our products. So we have Q equals I2, and this bracket is concentration, divided by the concentration of our reactants. So we have Cu2 plus, and we had a coefficient of 2, which means we have an exponent of 2 now, and that's going to be times I minus, which had a coefficient of 4, so it has a exponent of 4. And that's all you have to do. It's just simply writing out how it's going to look. Now let's move on to example 2. Consider the equilibrium reaction of H2 plus Br2 yields 2HBr. Which of the following correctly describes the relationship between Kc and Kp for the following reaction? So, take into account what our reaction is, the H2 plus Br2 yielding 2HBr. And we also have to remember how to compare Kc and Kp. It's going to be using the example or the equation Kp equals Kc times RT delta N, where delta N is going to be the moles of gas product, which in this case is 2 moles. So delta N equals 2 moles minus the moles of our reactants. So that's going to be 1 mole from the Br2 plus 1 mole from the H2. You know that when you add these together, so delta N equals 2 minus 2, so delta N equals 0. So we're going to plug a 0 in here. Which means it's going to cancel out this RT. So we'll be left with Kp equals Kc. And that's all you have to do. So you have to find the answer choice that matches this, which is going to be answer choice A. The substance H2SO3 is considered what? So, hopefully by now you'll realize that this is because we don't have that OH, but we do have the hydrogens, which shows us that it is an acid. Now we just need to determine, is this a strong acid or is this a weak acid? And so to do that, we need to look at the protons, which is going to be represented with our hydrogens, and compare it to our oxygen. So if our hydrogens are equal to or less than 1 of the oxygens, then it's considered weak. However, if our hydrogens have 2 or less than our oxygens, then it's going to be strong. So in this case, we have 2 hydrogens and 3 oxygens, so it's only 1 less, which means it's a weak acid, so it's D. But let's say that we had H2SO4. So that would mean that we have 2 less hydrogens than we do oxygens, which means it would be a strong acid. So because we only have one difference, for this example, our answer is D. Number 4. What is the pH of a 0.05 molar LiOH solution? So the first thing we need to realize is that LiOH is a base. So we know that it's going to be towards the upper part of our pH scale, so towards the 14 range. We also, let me go ahead and switch over to the boogie board. We also take into account that our equation for pH is pH equals negative log of H3O+. So we can plug in the molarity that it gave us. So pH equals negative log of 0.05 molar. When we plug this in, it says the pH equals 1.301. This corresponds with a strong acid. However, we know that we're dealing with a base. So all we do is take the top of the pH scale, which is 14, minus what we calculated, and we'll get our pH, which is 12.7, which makes sense. LiOH, it's a strong base, and 12.7 represents a pH of a strong base. Anything close to 14, strong. What is the concentration of H3O+ for a solution at 25 degrees Celsius that has a pOH of 5.640? So let's go and figure out how to compare pH and pOH. So we have pH plus pOH equals 14. We need to rearrange this because we know we can solve for the concentration of H3O+ by finding our pH. So we can manipulate this to where pH equals 14 minus pOH. And we were given pOH, so we can use that to solve pH. So pH equals 14 minus the 5.64, which is what it gave us, which gives us a pH of 8.36. We can now plug this into the pH equation to solve for concentration. So pH equals negative log of the concentration of H3O+. And this is what we're solving for. So let's plug in the pH we have. So 8.36 equals negative log of the concentration of H3O+. We can move our negative over, so we have negative 8.36 equals log of the concentration. And we know that log has a base of 10 because it has no number given. So to move it over, we say 10 to the negative 8.36 equals the concentration of H3O+. So we can solve for that, and H3O+'s concentration will be 4.37 times 10 to the negative 9. And that is our answer. All right. Farmers who raise cotton once used arsenic acid, which is H3ASO4, as a defoliant at harvest time. Arsenic acid is a polyprotic acid with K1 equals 2.5 times 10 to the negative 4, K2 equals 5.6 times 10 to the negative 8, and K3, which is 3 times 10 to the negative 13. What is the pH of a 0.5 molar solution of arsenic acid? So let's go to our boogie board. We know to solve for pH, we have pH equals negative log of the concentration of H3O plus. So we need to figure out what this H3O plus is to plug it in and solve for pH. To do this, we can use an ice table. But before that, actually, let's go ahead and do the ice table first. So we have our H3ASO4 and ice over here. So the initial concentration is 0.5. We're going to put it as generic products over here. So we have H3O plus and A minus as our products. We don't have anything initially of our products. Because we're going from reactants to products, we know that this is negative X and these are plus X. And then we bring everything down for our E. So 0.5 minus X, X, and X. So we need to find out what X is. So we can solve for K. But to solve for that, we need to know which K value to use. So we can use that pH equation one more time. When you plug it in, so pH of negative log of K1 equals pH of negative log K2 equals and pH of negative log K3. And you're going to plug the actual values that it gave you in the problem to solve for these. Let me move this in some. So when you plug this in, you'll get a pH of 3.6 for the first one, 9.25, and 12.5. So what you notice, arsenic acid is a strong acid, which means it needs to have a pH of an acid. 12.5 and 9.25 are not pHs of a strong acid. So the K that we're going to have to use is going to be K1, which K1 equals 2.5 times 10 to the negative 4. So we can now use that to set up our equation for our K. And remember, K, just like Q, is concentration of products divided by concentration of our reactants. So we say that 2.5 times 10 to the negative 4 equals the concentration of our product. So because we have two x's, we can just say x squared, divided by the concentration of our reactant, which is 0.5 minus x. You can rearrange this to solve for x. So you say that x equals the square root of 0.5 times 2.5 times 10 to the negative 4. Our x will equal 0.0112. So the concentration of H3O plus is x. So now we can plug it into our pH equation to solve for the pH we're looking for. So we say pH equals negative log of the concentration of H3O plus, which is 0.0112. So our pH is going to be 1.95. And that makes sense. We said that this was a strong acid, so 1.95 corresponds with the pH of a strong acid. Number 7. What is the pKa for the acid HA of a solution of 0.65 molar HA and 0.85 molar NaA, which is a base, has a pH of 4.75. So we know our base has a pH of 4.75. So let's go over to our boogie board. And the equation where we can compare pH and pKa is pH equals pKa plus log of our base divided by our acid. So we're given pH, so 4.75 equals pKa plus log of our base, which is 0.85, divided by our acid, which is 0.65. And we can rearrange this by subtracting this whole section right here to get it to the other side. So 4.75 minus log of 0.85 divided by 0.65 equals pKa. So our pKa will equal 4.63. Not too bad. You simply need to plug it in and solve for the variable. The hardest part is remembering the equation. Number 8. What is the mass of NaF? So remember mass because that's what we're looking for. That must be added to a 50 milliliter solution of a 0.5 molar HF solution to achieve a pH of 3.25. For Ka is 7.2 times 10 to the negative 4. So for this one, we can use that exact same equation. So it says pH equals pKa plus log of base divided by acid. However, they didn't give us a pKa, they gave us a Ka, so you have to use a second equation. So the second equation is pKa equals negative log of Ka, and they gave us our Ka. So pKa equals negative log of 7.2 times 10 to the negative 4. When we plug that in, we get a pKa of 3.14. So we can plug that in for our pKa. They gave us our pH. So 3.25 equals 3.14 plus log of our base, which we don't know, so we're going to put it as x, divided by our acid, which was 0.5. So we need to solve for that base, but this will give it to us in molarity, and we need it in grams, so we have to keep that in mind. So when I move this 3.14 over, I'll get 0.11 equals log of x divided by 0.5. So our x, which is our base, is going to be 0.644 molar, and that's moles per liter. So the first thing we need to do is get rid of those liters. So 0.644 moles per liter, which is molarity, and we had 0.05 liters, so our liters cancel out, and we'll have 0.032 moles of our base, but we don't want it in moles. So we need to do one last conversion to get from moles to grams. So 0.032 moles for every 1 mole, we're going to have about 42 grams of our base, which is just look on the periodic table and you'll be able to find and add up the weight. So we're going to end up with 1.3 grams of our base. Number 9. The indicator, purple red, has a Ka of 3.3 times 10 to the negative 6. What would the approximate pH range over which it would change color? So, to find the pH range, we have to have the pKa. So let's go ahead and calculate our pKa. So remember, pKa equals negative log of Ka. So negative log of 3.3 times 10 to the negative 6 is going to give us a pKa of 5.5. So by using our pKa, we say the pKa plus or minus 1 will give us our range. So the range at which it will change color is going to be 4.5 to 6.5. So this is the range at which we'll see color change. Number 10. The solubility of magnesium phosphate is 2.27 times 10 to the negative 3 grams per liter of solution. What is the KSP for Mg3PO42? This one's a little more difficult because there's multiple steps that we have to do. So if we have Mg3PO42 and we break this down, so it's going to break down into 3 moles of Mg2 plus and 2 moles of PO43 minus. Remember, your polyatomic won't break apart. And over here, I'm just going to write the weight of Mg3PO42. So Mg3PO42 is going to have a weight of 262.86 grams per mole. And that, just like before, you're just going to look at the periodic table, add all of the weights together, and you'll get the weight of our compound. So to find the molar solubility, we're going to have to take the solubility that they gave us and multiply it times the weight. So we take 2.27 times 10 to the negative 3 divided by the weight, which is 262.86, and that is going to give us 8.63 times 10 to the negative 6. So we're going to use this to plug in to find KSP. So KSP equals the concentration of Mg, because it had a 3 here, we put the 3 there, and then PO4 had a 2, so we put a 2 here. So we're now going to take this and multiply it by the numbers that were in front. So for Mg, we say 3 times 8.63 times 10 to the negative 6 equals, and that's going to equal 0.0000259. It's kind of long, I just wanted to write everything out. So this is what we're going to plug in for the Mg. So we're going to plug that in here. We're going to do the same thing, but for PO4. So instead of a 3, we put a 2. 8.63 times 10 to the negative 6. This is going to give us 0.0000176. And this is going to be for the PO4. So we're going to plug this in for PO4. When you plug it in and take into account the coefficients, our KSP will be 5.2 times 10 to the negative 24. There we go. And now we will move on to exam 3 sample problem. So exam 3 has less material. It's going to cover chapter 20, which covers thermodynamics, and chapter 21, which is electrochemistry. So example 1. What is the value of the equilibrium constant for the cell reaction below at 25 degrees Celsius? The E0 cell is 0.30 volts. So let's go to our boogie board. So we know that E0 cell equals RT divided by NF ln of K. Your R is a constant, your F is a constant, N is the electrons, and then K is a constant as well. It's not a constant, but you're going to be given it. So we need to rearrange this to where we're solving for K. So we're looking for this K value. So we can rearrange the equation by moving this NF to the other side. So we're going to have E cell times N times F equals RT ln of K. We need to do another step. So we're going to say E cell times N times F, and we're going to divide by RT on both sides to get rid of it on the right side, equals ln of K. And this way it makes it a lot easier to break it down to solve for K. So if you go back to our equation, we can determine what our N is. So we have a plus 2 and a plus 2, so N is going to be a 2. So N equals 2. Our R was a constant, so 8.314. F is a constant, which is 9.65 times 10 to the 4th. Our temperature was 25 degrees Celsius, which is going to be 298 Kelvin. So now we have pretty much everything we can use to plug in. And they also gave us our E cell, which was 0.3. So we say 0.3 times 2 times 9.65 times 10 to the 4th divided by 8.314 times 298. And that's going to be equal to ln of K. So if I solve for everything on our left-hand side, we're going to get 23.368 equals ln of K. To get rid of the ln, we're going to say e to what is raised on the left side will equal K. So this will go to e to the 23.368 equals K. So K will equal 1.4 times 10 to the 10. And that is our answer. All right, example 2. So kind of messed it up here a little bit. I'll have to read it to you because it kind of cut it off some. But what we have is elements of boron can be formed by reaction of boron trichloride with hydrogen. So we have BCl3 plus 1.5 H2 yields B solid, take into account, plus 3 HCl. And then it gave us our substances, so it gave us our S naught for each of these compounds. So we don't know what BCl3 is. Our S naught for the H2 is going to be 130.6. For B, it's 5.87, and for HCl, it's 186.8. It says if the delta S naught is 80.3 joules per Kelvin for the reaction above, what is the S naught for BCl3? So we're looking for that question mark. So let's go over here. So we know that delta S naught equals the concentration of our products minus the concentration of our reactants. And they gave us our delta S naught. So they said that delta S naught is 80.3 equals, so our products are going to be 3, because we had a coefficient of 3, times the 186.8 plus 1, because it didn't have a coefficient, which means there's a 1 there, times 5.87. And this is going to be our products minus our reactants, which I'm going to write right down here, which is 1.5 times 130.6 plus 1 times x, because we don't know what this variable is yet. So when you do this, it can simplify to 80.3 equals 560.4 plus 587. So this is our products right here, minus 195.9 minus x. Or plus x, sorry. So what we can do is we can condense it even more. So we say 80.3 is 370.37 plus x, and then we move this, equals right there. We move this 370.37 to the other side. So we're going to have x equals 290.1. So if we go back here, what goes in this question mark spot, so the BCl3 is 290.1. Number 3, calculate delta G naught for the reaction of the ammonia with fluorine. So it says, hint, you have to balance first. And it gave us all of our delta G naughts. So we simply need to do the products minus reactants. However, we need to balance it to figure out how many times we have to multiply the delta G naughts. So we have NH3 plus F2 yields N2F4 plus HF. And after working a little bit, we'll realize that there needs to be a 2, a 5, a 1, and a 6 for it to balance out properly. So now all we need to do is plug it into that equation. So we say 6 times negative 275.4, so this is part of our products, plus 1 times 79.9 minus 0, because anything times 0 gives you 0, plus 2 times negative 16.4. So when you plug all of this in, you're going to get negative 1,539.7 kilojoules. And that would be our answer. Number 4. Use the given data at 297 Kelvin to calculate, this should be delta, so ignore the D, delta G for the reaction. Cl2 plus SO2 yields SOCl2 plus Cl2O. Hint, you have to balance it again. So let's go over. We have Cl2 plus SO2 yields SOCl2 plus Cl2O. After trying to balance it, we'll get 2, 1, 1, 1. Pretty easy. And we're trying to find delta G naught. And we're given delta H's and delta S's. So delta G naught equals delta H naught minus T delta S naught. So we have to figure out what our delta H is and our delta S is. So multiple steps on this one. So for delta H, all of them going to be products minus reactants. So we have it's going to be 80.3 plus negative 202.5 minus 0 plus negative 296.8. So our delta H, once you do all the math, will be 164.6. So this will get plugged in right here. Now for delta S. So delta S naught, we're going to have 266.1 plus 309.77 minus the 248.1 plus 446. So do take it into account that I just multiplied it by 2 already because of this. So our delta S is going to be negative 0.11823. And so now I can plug it in. So delta G naught equals 164.6 minus our temperature, which is 298, times our delta S, which is negative 0.11823. So our delta G naught is going to be 199.8. So it's a lot of steps, but it's pretty much the exact same thing we've done before. You just have to do multiple things. All right, number 5. Which one of the following pairs of substances could be used to construct a single redox electrolyte, i.e., they have an element in common, so the elements have to be in common, but different oxidation states. So let's look. So for A, we have HCl and Cl minus. So when we break it down, it becomes Cl minus and Cl minus. So they have the same state. However, the oxidation state or the charge should be different, which means this A cannot be our answer. For B, we have H plus and OH minus. This one is pretty much already broken down as far as it can, so it stays as H plus and OH minus. So the charges are different, which is what we're looking for. However, the elements aren't the same, which means B is not our answer. C, we have H2O and H plus. When you do this, it goes into OH minus and H plus. So just like we said before, the charges match because they're different. However, the elements are supposed to be the same, so C cannot be our answer. For D, we have Fe3 plus and Fe2O3. When we break down the Fe's, we get Fe3 plus and Fe3 plus. So the elements are the same, however, the charges are supposed to be different. So D cannot be our answer. So finally, we're going to look at E, which is MnO2 and Mn2 plus. When we break it down, we get Mn4 plus and Mn2 plus. Elements are the same, charges are different, which means E is our answer choice. Number 6. The redox reaction of pre-oxydisulfate with iodide has been used for many years as part of an iodine clock reaction, which introduces students to kinetics. If delta naught cell, E naught cell equals 1.587 volts and E naught of the cathode half cell is 0.536 volts, what is the E of the anode half cell? So, let's go over. The equation is going to be E cell equals E cathode minus E anode. So, when we do it, we can rearrange it to get the E anode by itself. So we get E anode equals E cathode minus E cell. And they gave us our E cell and they gave us our E cathode, so all we have to do is plug it in. So our E anode is going to be 0.536 minus 1.587. So our E anode is going to be negative 1.05. And that's our answer. 7, sorry. If the electrodes of a voltaic cell are connected with an external wire, electrons will flow in the wire from the cathode to the anode. True or false? This one, you just simply have to know what it looks like. So if you don't remember what a voltaic cell looks like, go back, look, and see how the electrons are flowing. For this example, it's going to be false. In a voltaic cell, we're going to have our electrons move from anode to cathode. Number 8. The lead acid battery is an example of a secondary battery. True or false? This one is true. A lead acid battery is going to be something such as a car battery. And a car battery can be recharged. And for something to be rechargeable, it has to be a secondary battery. So true would be for this answer. And this one is a bit time consuming. It is going to be a half reaction. So it says, what is the coefficient of H2O after performing a half reaction on the following? And show all of your steps. So let's go to our boogie board. So we have the reaction of MnO4 minus plus Cn minus yields MnO2 plus CnO minus. First step is to break it up into its two half reactions. So we have MnO4 minus yields MnO2, and we have Cn minus yields CnO minus. So we now have it broken up into our two half reactions. Step 2. There's multiple parts for this one, so we're going to break it down. The first part is to balance the atoms other than oxygen and hydrogen. So this is going to take into account our Mn and our Cn. So they're already balanced, so we can just rewrite it the same way. So MnO4 minus yields MnO2, and Cn minus yields CnO minus. The second part to this one is going to be to balance your oxygens by adding water. So we have 2 more oxygens on our left side than we do our right. So we need to add 2 waters to the right side. So we have MnO4 minus yields MnO2 plus 2H2O. For the second one, we have 1 oxygen over here and we have none here, so we need to add a water to the left side. So it becomes H2O plus Cn minus yields CnO minus. The third part to step 2 is going to be to balance your hydrogens by adding H plus. So because we added water, we now have 4 hydrogens on the right side. So we need to add 4 H pluses to our left side. So we get 4 H plus MnO4 minus yields MnO2 plus 2H2O. Same thing we're going to do because we added 2 hydrogens here, we need to add 2 H pluses to our right side. So we get H2O plus Cn minus yields CnO minus plus 2H plus. And then finally, the last step for step 2 is going to be to balance our charges. So you have to add the charges that you have on both sides. So we have 4 positive here, we have 1 negative, and we have nothing over here. So to balance the charges, you have to add electrons. So for the first one, we need to add 3 electrons to our left side to get it to balance the 0 charge that's on our right. So we have 3E minus plus 4H plus MnO4 minus yields MnO2 plus 2H2O. And then down at the bottom, we have a negative 1 charge here, but we have a negative 1 and a plus 2 here. So we need to add 2 electrons to our right side to get them to balance. So this one will become H2O plus Cn minus yields CnO minus plus 2H plus 2E minus. And I'm going to erase this, but rewrite this section in just a moment. So we had 3E minus plus 4H plus MnO4 minus yields MnO2 plus 2H2O. And we also had H2O plus Cn minus yields CnO minus plus 2H plus 2E minus. All right, so this was what we had after step 2. Step 3 is going to be to balance our electrons. So we have 3 here and we have 2 here. So we have to find something to multiply to get these electrons to equal each other. So for this one, we can multiply by 2, and for this one, we can multiply by 3, and we'll end up with 6 electrons at the end. So we end up with 6E minus plus 8H plus 2MnO4 minus yields 2MnO2 plus 4H2O. And that's for this top one. And then for the bottom one, we have 3H2O plus 3Cn minus yields 3CnO minus plus 6H plus 6E minus. Now, for step 4, you need to cancel out the items to simplify it and then add it together. So for step 4, our electrons can cancel. We have 6 canceling out here, which means we'll have 2 left. Our waters will get canceled out here, so we'll be left with 1 water there. And so far, that's the only things that can get canceled out. So when you rewrite it, you get 2H plus 2MnO4 minus plus 3Cn minus yields 3CnO minus plus 2MnO2 plus H2O. And they wanted to know what the coefficient for the water was. So our water, there's only one, so our coefficient of water is going to be 1. All right, well that wraps up pretty much everything that we have for this exam review. So I highly suggest that you go back through all of your notes, and I hope that this video was helpful when studying for your final. Thank you and have a good day.